Well, let's finish up with the symmetry part. So we want to check for symmetry. There's two M's in there, symmetry. Boy, that's ugly. Let's write that again, symmetry. That's not much better, but it's a little better. Symmetry. Okay, so let's take a look at our original equation here. So what we were given originally had an f of x with it, right? I'm going to get rid of this. So what we had originally had an f of x in it. We're going to talk about functions in general in just a second, but for the purposes of what we've already done, we can just write this with a y. If we want to check for x-axis symmetry, we're going to just do what we did back in that section with relations. I think it was section 1.2. Yeah, it was 1.2. So we're just going to put negative y for y and check equivalence. Okay, so we just put the negative in there for y. And we see, hey, is it the same? And really, really quickly, we can see that it's, well, just not the same. So it's got no x-axis symmetry. Okay, so it's got no x-axis symmetry. We want to check for y-axis symmetry now. We're going to put negative x for x and check for equivalence. We could probably see into the future here. If we put a negative there, we're going to square it. It's going to become positive. So maybe you'll write this in your work. You probably should, but it's likely that we can see it ahead of time. Okay, so we square it. We get 6 over x squared plus 3. And lo and behold, we have the same thing. So this is equivalent. And it does have y-axis symmetry. Okay, it does have y-axis symmetry. Now we should test for origin symmetry as well. So we test for origin symmetry in the same way, right? We're going to put negative x for x, negative y for y, and we're going to check for equivalence. So if we put in a negative y for y and a negative x for x, we're going to see what happens. Well, the negative y, nothing's going to change there, but this one does become positive, just like it did on this other side over here. So this now, we want to compare this guy to what we had originally. Well, we got a negative y instead, don't we? So we would say no origin symmetry. Okay, so it's not symmetric about the origin. Okay, so we found that this thing does have y-axis symmetry, and that confirmed our suspicion about what was going on with the graph, right? It looked like it had y-axis symmetry, and we've just verified it analytically. Now let's talk just a tiny, tiny bit about what we did here. So we needed to have f of x, right? But those are the same thing. We know that y is equal to f of x. So in our notation, when we're talking strictly about a function, we can streamline this process. If we're talking about a function cannot have x-axis symmetry. Let's go to this little box down here. A function cannot have x-axis symmetry. When we define what a function was, it was a relation in which no two domain values are repeated. Or another way to say that would be for each x value, there's exactly one y value. So that means that there can't be two ordered pairs that share the same x value that have a different y value. And this is exactly what we talked about when we talked about symmetry. So if a graph is symmetric about the x-axis, it cannot be a function, right? So we don't even really have to worry about x-axis symmetry, and we can just kind of streamline our process here. Because really, all we're going to do to check y-axis symmetry is put in a negative x, and what happened? So we put in a negative x, so essentially this was figuring out what f of negative x was, and we found that this was the original function, right? So if a function has y-axis symmetry, then this relation must be true. And the other way around, right? If this relationship is true, then it has y-axis symmetry. And let's take a look at, well, I guess we didn't have origin symmetry here. But if we did, this is what would have to be the case. We remember when we were looking at origin symmetry, here's my point that's symmetric to it. If we wrote this with function notation, this would be x comma f of x. And if we wrote this with function notation, we would have negative x comma negative f of x. So we would need these two things. We would need these two things to be the same. Oop. Okay, so these two objects need to be the same for origin symmetry. So we can absolutely talk about these things, symmetry that is, independent of the function language, and sometimes it's easier to do that, but sometimes, and in this case is one of those cases, I think, it's probably easier to think about it with with the function notation. So if we can show that this relationship is true, if f of negative x is equal to the original thing, then we've got y-axis symmetry. And if we put a negative x in there and then we get the negative of what we originally had, then that's going to tell us that we've got origin symmetry. But if we wanted to just put a y instead and think about it as just a general relation, we can absolutely do that too. But in the case of a function, you're never going to find x-axis symmetry.